The last specific force we're going to talk about is the spring force. And so spring forces are forces that exist whenever we have a spring being stretched or compressed. It also can apply to rubber bands or elastic bands or other stretchy things. One unique thing about the spring force is that it varies based off of how much the spring is stretched or compressed. And we haven't really seen that before, but if you think about having a spring, the more you pull it, the more you stretch it, the more it pulls back. Okay? And so that's going to be a unique thing about the spring force. One other thing about the spring force is the direction of the force. So the direction is always going to oppose the direction it's stretched or compressed. So we see here that this spring has been stretched out to the right, which means that it's going to exert a force on this box going back to the left, opposite the direction it was stretched or compressed. Last thing about the spring force is how we characterize it, and that's with this constant K. So K is the spring constant. It really represents how strong the spring is. So it's measured in newtons per meter. So it represents how many newtons of force you need to exert on a spring to stretch it or compress it 1 meter. Okay, so really it's a measure of how strong the spring is. So if we have something like the spring in your pencil, in a mechanical pencil, it's going to be a very low spring constant, whereas the suspension in your car, a much stronger spring, would be a high spring constant, a much higher K value. Mathematically, springs obey Hooke's law, which is outlined right here. And what it does is it tells us that the force that a spring exerts on an object is equal to K, that spring constant that we were just talking about, which really measures how strong the spring is, times X, the distance that the spring is stretched or compressed. Sometimes you'll see it written as delta X, because it's really the change in length of the spring, but oftentimes I usually just write X. So Hooke's law, just a quick story, was named after Robert Hooke, who was a famous scientist at the time of Isaac Newton. And Hooke and Newton actually had a few very public and very famous feuds. They did not like each other very much. In fact, Newton's one famous quote that says, "If it appears as though I have seen further is because I was standing on the shoulders of giants," is actually meant to be a veiled insult, a veiled 1600s insult at Robert Hooke, who was very short and had allegedly stolen some of Newton's work on optics, hence the "if it appears as though I have seen further." Anyway, this is Hooke's law. This tells us how much force springs exert on objects. Okay, K, our spring constant, times X, the distance stretched or compressed. You will sometimes see it written as negative Kx, and that simply is indicating that the force and the displacement are in opposite directions, like we talked about on the previous slide. I just do F equals Kx, and you're finding the magnitude, but you will see it the other way sometimes. Starting with our first practice problem here with spring forces, we have an ATV dragging a 45 kilogram log across a field using a spring. We're told the unstretched length, we're told the coefficient of friction, lots of good things here. So I'm going to first start with drawing my free body diagram. I, of course, have the force of gravity acting on the object and the normal force because it's being pulled across a surface. In this case, the thing pulling it is not just a regular pull, but a spring force specifically. It doesn't explicitly say this, but we're going to assume the spring is pulling on it horizontally. Otherwise, we wouldn't be able to do the problem. And then we're going to have the force of friction. So as always, I'm going to set up my max and my may. I'm going to start with my may. So in the y direction, I have my normal force, and I have the force of gravity. And that's going to be equal, in this case, to 0, because I'm not accelerating vertically, perpendicular to my surface. So that means that my normal force here is simply going to be equal to gravity, which is mg. So my normal force is going to be 45 times 9.8, which is 441 newtons. Moving on to my x, the forces I have in my x direction, I have the spring force, and I have the force of friction. So it's going to be the force of the spring minus the force of friction equals max, because I do have an x acceleration of 2.3 meters per second squared in the direction of the spring force. Substituting in for both of these forces, actually, for the spring force I can say kx. For the force of friction, kinetic in this case, since it's sliding, I can say mu k times my normal force. And that's going to be equal to max. I'm going to go ahead and just sub in everything that I know. I know my spring constant is 500. I don't know my x, that's the distance stretched to compressed. So although I know this unstretched length of 0.75, x is actually the change in length. So I'm going to leave that as an x. Mu is 0.68 times the normal force that I just found here of 441. And that's going to be equal to 45 times my x acceleration, which is 2.3. So what I'm left with here after I simplify is 500x minus 299.88, which is the force of friction, equals 103.5. And I go ahead and solve for x, and I find that my distance stretched or compressed is 0.807 meters. To finish this and solve for the new length, I'm just going to say that length, which I'll call L, is 0.75, my unstretched length, plus the amount it's stretched, 0.807, and so I get a new length here of 1.557 meters. Moving on to our last spring problem. So we have a graph here showing the force required to stretch a spring a given distance. What we first want to do is figure out what the spring constant is. So what I'm going to start with is starting with that known relationship, that force is equal to kx. So force is on the y-axis, as we see, and the distance stretched here is on the x-axis. So I'm going to think back to that part of the linearization unit when we were looking at the relationship between variables and what the graph would look like if we were to graph those two variables. And the first thing we always did was we always isolated what variable was on the y-axis. And so we actually already have that here. The force of the spring is on the y, so that's already isolated. And then we're going to pull out any constants and match this up with the equation of a line, because that's what we do have here. We do have a linear graph, and that's important. So we're going to match it up with the equation of a line, y equals mx plus b. And we see here that the spring force matches up with our y, that's what's on our y-axis. The distance stretched matches up with our x, that's what's on our x-axis. And that simply means then that our slope, in this case, is equal to k. So in that first question, when it's saying, what is the spring constant, we simply want to find our slope. So in order to do that, I'm going to pick some points here. So I'm going to pick that first point there, 0.1, comma 200. And I'm also going to pick this point up here, 1, comma, and it looks like this is going to be 1200 because each one of these is 200. So we go ahead and solve for our slope here, and we end up having 1200 minus 200 over 1 minus 0.1 on the bottom for our change in x. And so we end up getting a slope which is equal to our spring constant of 1,111 newtons per meter. So there we have our spring constant. If we think about the units for a second, those units actually match with what we are seeing on our graph. What we did was take the slope, the y over the x. The y was in newtons, the x was in meters, and so we end up getting units of newtons per meter for our slope. Moving on to part B, the second part of this question, we're asked to explain why the graph does not intersect right at the origin. We can clearly see it intersects a little bit above it. And so there's a few reasons that we could come up with for this one. The first and the easiest is uncertainty. Anytime we're taking actual data, there's always going to be uncertainty in our measurements. And so that could be one reason why we don't have that perfect intersection right at 0, 0. Another is this could be not an ideal spring. Okay, we make the assumption that it obeys Hooke's law completely, but that might not actually be the case. In reality, some springs take a little bit of force to make them begin to stretch. And we see here from the graph that we need about 75 to 100 newtons of force before this spring even begins to stretch. So even though Hooke's law tells us that when the distance stretched is 0, the force should be 0, in reality this could be a spring that does not perfectly obey Hooke's law. There are probably some other reasons we could come up with here, but I think those are the main two, the two most likely reasons why it doesn't perfectly intersect 0, 0.